Our project was about building a mobile app to help researchers, tourists, and residents of the Galapagos Islands identify birds by recordings of their calls. It's very exciting for tourists, it's extremely important for researchers to monitor bird colonies, and it's a fun way to incentivize locals to engage in conservation activities. The app has an educational aspect as well, as it's designed to give users some insight into how AI algorithms could recognize bird songs.
This is what the user sees when they open the app. Pressing the record button for the first time will prompt the app to ask for mic and location permissions. The general pipeline is that the user hears a birdsong and records it by pressing the record button. The recording is sent to a server which identifies the bird and returns it to the user. The app then displays this result to the user with a visualization of the processing done. We can press the cancel button to start a new recording.
Before showing you the actual prediction made by the app, we'll first explain more about how we trained the model and set up the server.
The standard method for audio classification is to use a short-time Fourier transform to obtain a MEL spectrogram, an image showing intensity in each frequency over time, then use image classification neural networks. For example, this spectrogram is generated by the sound. One major issue we ran into was denoising, so we used techniques like median clipping, adaptive thresholding, and morphological operations on the images. We expanded the dataset and simulated some real-life issues using augmentations like blur, dropout, and random noise, producing several labeled data points from one image. And it was crucial to locate the birdsong in long recordings. For this, we denoised, binarized, removed small components, and used a windowing algorithm as shown.
To exploit the locality of different species, we added GPS data to our model in the form of altitude, longitude, latitude, and island name. In doing so, we faced several challenges, including filling missing GPS entries for training data, adding noise to avoid overfitting, detecting tiny islands, and finding the optimal balance between GPS data and audio data in the neural network.
The neural net has a convolutional layer to extract pattern-based features. Here are some example filters. We can see them matching these sections of the spectrogram through the process of convolution. The convolutional layer is followed by a max pooling layer that keeps only the maximum values from the convolution. These values are what finally contribute to the prediction probabilities. With the integration of location data, however, these probabilities are also affected by the GPS location and which island the recording was made on, so it has the potential to sway the prediction in some other direction. Here is our final neural network design.
When one of our users hears a bird call, they pull up our app and begin to record it. This recording is sent to our server, which spawns a new thread to save it, as well as the user's GPS data. We then call our Python scripts to convert the file into the format necessary and encode our GPS data into an island and feed all of that into our neural network. Then we get back a list of probabilities which we sort. Finally, we send back what bird it classified as, the probability, and a picture of their spectrogram. We needed our server to support both Android and iOS, so we only used simple sockets. To be able to transfer the data to our Python processes and to do all of that in a thread-safe manner.
Now returning to the app, this is the result of the prediction displayed along with some useful and educational information.
Thanks for listening. The six of us greatly enjoyed this project. We're excited to see how our app is used in the coming months.